extension of things that you already know. Some properties of exponents. We already did a whole bunch of stuff with properties of exponents twice this year. And you guys are very good with that. You know that, for just a quick example, if you multiply like bases, what do you do to the exponents? Add them. If you divide like bases, you subtract. If I take a power to a power, I multiply the exponents. Good. Etc., etc. The only difference here in this new stuff is we're going to look at the exponents that are not integers necessarily. They could be fractions. And why would that happen? Okay, well, when you see roots like this, now, what does that say? What is that thing right there I'm pointing at? How would you say that? It's not a square root. It's a fifth root. Well, what in the world does that mean? Square root, we know that the square root of 9, and really there's an invisible 2 there that we just don't write, is what? 3. Because 3 squared is 9, right? Okay, and by extension, we know that the cube root of 27 is what? 3. Because 3 cubed is 27, right? You get the idea. So if I take a big root, it's no different than a small root. It just involves a larger power of x is all, or power of, maybe not x, larger power of a number. If I do something like the 6th root of 64, what to the 6th is 64? Do I know? 2. Yeah. Okay. See how that works? All right. So that's what this is. How does that relate to exponents? Well, it turns out that whenever you write a root or radical, whatever you want to call it, of something, you can also write it as a fractional exponent. That 5 ends up in the denominator of the power. So that's the same thing as saying 13 to the 1/5 power. Okay? So whatever sits, we call this the index. Whoops, this pen is getting so bad. The index of the radical is that number that sits out on the radical sign. That is what always goes in the denominator. Now, if I have something like this, what if I had the 4th root of 7 cubed? What kind of fraction do you suppose that would be? Where's the 4 going to go?
Underneath.
On the bottom. Where's the 3 going to go? On the top. Absolutely. That's just a normal power there, isn't it? 7 cubed. So that looks like 7 to the 3/4. Okay? And you can enter it in your calculator that way. In fact, it honestly is the quickest way to do a root other than a square root is just to take it to the power of 1 over the index number. Okay? All right, so there's one little tidbit. Now, how do we use this? You know, there are all kinds of things we could do with this, but really the one that you're likely to use is a situation like this, where you want to simplify some big radical involving numbers and exponents and all that stuff. And this is not a big deal. I'm going to show you a great trick. If you just pay attention big time here for the next couple minutes, you're going to learn a trick that's going to help you for years. This really is a good one. So here's how you do this. Okay, what we're going to do is we're just going to break this up into pieces. We're going to break it up into the logical pieces. We've got the number part, the x part, the y part, and the z part here, right? So let's separate this out into the cube root of 128 times x to what fractional power? Well, the 2 over 3. Okay, now here's the index, right? So that's always going to go in the denominator, right? So I'm going to get, well, yeah, but we're going to deal with the number separately. The number is honestly the hardest part. The variables are really easy. So this becomes x to the 2/3. Everybody see that? Okay. We get y to the what?
Third.
9/3. Okay, good. I'm going to write it that way for now. And some of you guys are already seeing a shortcut there. Times c to the 16/3. Okay, good. All right, so we got those 4 parts. Now let's deal with the number part first. How about that? Really is the hardest part. All we've got to do here is the same process that we've done all year with square roots. When we want to simplify a square root, remember how we did that? Let's just quickly review, take an example using square roots. If we had something like, say, the square root of 75, we wanted to simplify that. Remember, our goal was to find the biggest perfect square that divides evenly into 75, and we'll split that 75 up into a product of the biggest perfect square and whatever's left over, whatever's left behind. What is the biggest perfect square that divides into 75? What is it? 25, sure. 25. So we could break that up into the square root of 25 times the square root of, what's 25 times what is 75? 3. Okay. And then the square root of 25 becomes 5. All right. So that's the part that gets released from the radical, and then we're left behind with a 3 inside the radical, right? So all we needed to do was find a number, a perfect square, right? Now, in this case, we're not dealing with squares, we're dealing with cubes. So we got to find a perfect cube. Perfect cubes they're not right so available in our memory. So we might even want to make a quick list of those. I will even give you a list. In fact, I have. There's already a list on Moodle that I'll print out. Next time we're in the lab, I'll print it out for everybody. It's got perfect squares and perfect cubes, and I think perfect fourths up through just the small ones that we'll need. If we look at perfect cubes, what's 2 cubed? 3 cubed? 4 cubed? And we could probably stop there, couldn't we? Because 64 goes into 128, doesn't it? Okay, so we could break this up into then the cube root of 64 times the cube root of what? 2. 64 times 2 is 128, right? Okay, so the same idea we had with square roots. Now here's my trick for the exponents. All you have to do with the exponents, once you've written them as fractions, you're going to turn those fractions into mixed numbers, right? Like for example, if we had something like 13 fourths, and I wrote that as a mixed number, what would that be? 4 goes into 13 how many times? 3 with how many left over? So remember that stuff? We don't usually do this anymore. I've told you not to ever use mixed numbers except in this one little trick. That's a mixed number. Now when we take these fractional powers and we write them as mixed numbers, what the advantage of that is that the integer part is the power that goes outside of the radical, and then this is the part that's going to be left inside the radical, right? So x to the 2/3, well, as a mixed number, just stays x to the 2/3. 3 doesn't even go into 2, right? So this one stays the same. What about y to the 9/3? 3 goes into 9 3 times evenly, right? So that's just plain old y cubed. What about the z? 3 goes into 16 5 times and 1/3 left over. Okay. All right. So once we've done that, we're home free. Whoops. Okay. So then now our answer is going to end up looking like this. We're going to have something out front times the cube root of the stuff that's left inside. Here's where we start separating things. The cube root of 64 we said was 4. Okay, so that goes out there. But the 2 is left inside, right? Okay, what about the x's? Well, as a mixed number, there was no integer there, so the x squared stays in there, right? Because that's x to the 2 thirds, right? So we're just moving back, instead of writing it as a fraction, now we're moving back to writing it in radical form. Okay? What about the y cubed? Where does that go, do you suppose? Outside, yeah. And then the z to the 5 thirds? Both. We get the 5, the z to the 5 goes on the outside, and the z to the 1/3 goes inside, right? There's my z to the 1/3. See how that works? Do we even write that 1? No, we don't. Okay, whoops. You get the idea? That, my friends, is a pretty good trick. You know that you save a lot of hassle having to go through this sort of more traditional way. That really works well. Let's try one more of those. I feel like that makes sense? Okay, so just split it into separate parts. Okay, try that one real quick. Yeah, I'll put it up on Let's make a quick list of perfect fourths. How about 2 to the 4th is 16. 3 to the 4th. Now, when you do fourths, for example, 3 to the 4th is just 3 squared, isn't it? Right. So you can just square the square. It's a good little trick. So this would be 3 squared is 9. Squared is 81. 5 to the 4th. 5 squared is 25. Squared is 625. Those grow pretty fast, you can see. Right? So obviously we only need a couple there, if any. Which one of those might be important here? 81, yeah. Okay. Okay, what do we get for the number part? What does the 4th root of 162 break up into then? Okay, good. Because then we can split that one, can't we, into the 4th root of 81 times 4th root of 2, 81 times 2, and then that just becomes 4th root of 81 is our 3. And we got a 2 stuck under the radical, right? Now the exponents, easy. What's the fractional power of x up there? Okay, true, but we actually want to leave it in terms of, I see what you're doing, you're simplifying the fraction, reducing it. We want to leave it in terms of fourths, though, because that's what the radical. Okay, good, so x to the 2/4, so we would end up with an x squared inside the radical. That's stuck there. We can't. None of that comes out. What about the y's? What's our power of y? Okay, good. We get a y to the 9/4, and as a mixed number, that becomes 2 1/4, right? So we're going to get a y squared and a y to the 1, which we wouldn't really have to write. I'll just put it right there. Right? It's invisible. Right? 2 1/4. And then the z, yeah, 16/4 is 4. So that all goes out front. That's it. We're done. Okay, oh, now how would we enter that on Moodle? Okay. On Moodle, there is no, when you're entering stuff, and I put these into the algebra type questions where you have to enter an algebra expression. But there is no way to enter we can do squirt for square root, but there is no equivalent of squirt for cube roots and fourth roots and all that stuff. So how would we have to enter this in Moodle then? How would we enter a radical like that? What do you think? All we really could do is enter it as a power. What would the exponent be? Ah, yeah, 1/4, wouldn't it? Right? So in Moodle, we just enter this as 3y squared z to the 4th times the quantity 2x squared y to the 1/4. Okay. Well, the only part that's different is, that 4th root we just would enter as a 1/4 power. Okay. All right. Moving on. Okay, the rest of this stuff is really, there's nothing that you don't already know. How do we do that? So what if they're fractional exponents? The same rules always apply that have applied before. What do we do there? Yeah. Well, what's the 3 times 5 going to give us? 15. Yeah, we're going to get 15 from the number part. And then if I multiply like bases, what do I do to the exponents? Add them. Yeah. So I get x to the 1/3 plus 2/3. What's that? 1. So it's 15x. Okay? What about that? Yeah, I'm dividing ugly-looking fractional exponents, but still, they're just exponents. So what do I do in a situation like this? Well, the 2/4 reduces to, okay, 1/2. And then what about, we want to write this in terms of positive exponents, right? Positive integer or rational, meaning fractional exponents. What's bigger, 1/2 or 1/5? So where's the x going to stay then? On the bottom. When I divide, what do I do to the exponents? Subtract. So I get 2x to the 1/2 minus, I can read that, 1/5. Well, 1/2 minus 1/5, we've got to do a little subtracting of fractions. How do I do that? Yeah, okay, I'm just going to get a common denominator, right? So I could multiply, what would my common denominator be with 2's and 5's? 10. So multiply by 5/5 and 2/2. And that's going to give me 5 minus 2 over my common denominator of 10, 3/10. Which I honestly, even with decimals, I could get here, couldn't I? 1/2 is 0.5, 1/5 is 0.2. What's 0.5 minus 0.2? 0.3, right? 3/10. Either way, I get 1/2 times x to the 3/10. That's my answer. Okay. Same rules as before. Only difference is we're adding and subtracting fractions this time. Which I know people don't necessarily like to do, but they can do. Okay, so that's the first assignment right there. Not much to it. Now, you may want to even do it more than once if you want to. That's fine. Even if you get 100, if you want to go back and try some additional problems, that's fine. They're there. Kind of leave that up to you. I know you guys are busy, but just to get ready for the test. Let's take a look at